We have also a huge number of planes, but there are 3 planes that are in particular interesting. This will be so-called 100, 110, and 111. The next topic is crystals. In this part, I would like to discuss the concept of lattice, primitive vectors to construct lattice, unit cell, brevet lattice in 2D and 3D, lattice base, and then go to silicon. This is something that will be really interesting, and we will be coming back to these topics later. So silicon lattice as sp3 hybridized, the unit cell of silicon, and the planes is in crystal. And planes in the silicon crystal will be really interesting. Sometimes the way we cut the wafer for given application, it's really determined by characteristics for a certain given plane. And then there is a topic that I would like to just guide you into the topic of the inverse room and case space in order to be able to just speak about EK diagrams. And this is useful to understand the fact that we have these direct and indirect bandgap semiconductors, and also the topic of effective mass and how actually it can change for the different planes of the crystal. What is a crystal? It will be a periodical arrangement of atoms or molecules in 3 dimensions. Here I'm cheating a little bit because I'm showing a periodic structure using a molecule as something that in the previous part we saw it was model of silicon atom, but you will see that the lattice with silicon atoms, it's actually not looking like that. It's just to start with the concept. It's a 3D structure, and we will also speak about unit cells, which when translated by the primitive vectors they build, construct the lattice. And again, for silicon, the unit cell is not looking quite like that with the 8 atoms. It will be a bit different, but just a bit patience, and we see in the coming slides. So we take these unit cells and we translate it to form the bigger structure, so infinite, in fact. When we talk about lattice, very often we like to talk about infinite because then we don't have the boundary conditions and edges that cause some problems. But the fact is that, for example, where we have MOSFET transistor, it's all the surface conduction, and just above there is the gate oxide. So we still have to keep in mind that at some point we have these boundary effects. So we obtain lattice by this translational arrangement of the shift of the lattice points. So what we have here is the lattice in 2D. There are some points, and there are several ways how we can obtain them. So starting with a point which will be our, let's say, at 0 location, we can translate it, for example, by vectors A1 and A2. And like that, we can form this whole lattice, actually infinite lattice. And primitive vectors for this lattice are such that can actually construct them. And in this case, we can see that with C1 and C2, we can also form this lattice. With D1 and D2, we can also form the same lattice. But for example, B1 and B2, that's a bit misleading. With these 2 vectors, we cannot construct the given lattice. So not all the possible vectors connecting the points are the primitive vectors, but there is a large selection of such primitive vectors that form the lattice. But usually we would choose the things that are most symmetrical and most obvious, like A1 and A2. Okay, so we have these primitive vectors, we have periodicity of the lattice, And then what we also need is a unit cell, because it's the unit cell, each containing, in this case, each unit cell contains just one lattice point. It overlaps here, for example, with 4 lattice points, but the right thing to say is that we translate this unit cell with a single point by the lattice vectors, the primitive vectors, and actually cover the whole 2D plane. In the crystal, in 3D crystal, we talk about the volume. And this unit cell has to be chosen in such a way that it doesn't have any overlaps or doesn't create any voids. So quite, for these very simple examples, it's very intuitive, I think, what we're talking about. And then this unit cell that can also look, for example, like that or like that, but always it has just one lattice point. We translate it by the primitive vectors from the previous slides. If we have the integer number, then with this formula we can cover the infinite space and create the 2D lattice. If we include the green text, then we also go to 3D and we cover the whole volume to create a Breve lattice. Then in 2D, we can speak about 5 different Breve lattices, which you have shown here. In fact, the last one, it's very similar to the first one. The differences are the angles and also the edges. Here it will be A and A, the same edge on both sides. Here it will be A and B, so different dimension. We can consider, for example, such lattice that quite intuitively we connect into a honeycomb. And this won't be a Breve lattice because we don't have such selection of vectors that, given the previous conditions, translating by the integer number by these vectors, we won't be able to build the space without any voids and overlapping. So in this case, actually what we have is the lattice base, which is formed of 2 points, and we translate this lattice base to create the lattice, but it won't be still a Breve lattice. For 3D, we have 14 Breve lattices, and some of them that are very popular is the simple cubic, or body-centered cubic, or face-centered cubic. And the face-centered cubic is the one that is interesting for us because that's the Breve lattice that resembles the silicon. So if we want to have a crystal, we already know the lattice, that's the mathematical concept, and then we need also a base. And the base can be an atom, but can be also a group of atoms, can be a molecule, can be formed of several different atoms. So for example, for a rock salt, what we have is the base made of 2 atoms, Na and Cl. And when we take this lattice and fill it with the base, then it looks like that. That forms the crystal of the salt. And here we can also identify some symmetrical structures within the lattice. When we talk about the silicon, first of all, before we even go to the lattice, we look at the bonding that it forms with other atoms. And the bonding is called sp3 hybridized. So I will explain where the name comes from, and then it won't sound like it's difficult to even remember. So it has the 4 covalent bonding, which goes to 4 neighboring atoms. And this structure, it's called tetrahedron structure. That's the bonding unit of atoms with an atom inside and then the 4 neighbors around. So when we copy it, we translate this tetrahedron, we can see that it forms the certain structure Now what I'm going to do in the next slide is to rotate it. But let's first explain what is this tetrahedron. When we have a single silicon atom, there is inside here in this ball also we include the earlier shells. So I'm starting the analysis with the valence shell. And normally, because we have just 4 electrons, the S shell will be filled, and then the P shell will be filled, and then those 4 electrons are missing in the valence band, and they can be later coming from a different atom to form the covalent bonding. But that's the situation with a single atom. Now, if we have 2 atoms or more atoms in the crystal, what happens? Now I should change the green color from to something else, because in the first case it meant an empty state, unfilled. But here it means that it's complemented by atom, the neighboring atom. And what happens here is that all 4 of the electrons in the left-hand side and the right-hand side atom, they will be forming covalent bonding. In fact, not with the same atom. I should draw 4 atoms. But each electron forms covalent bonding, so they will all share the same spin for a single atom. And then we have the spin down from a different atom. So in fact, the atom has S and P3. And that's why it's sp3. So when we rotate this structure slightly, we can identify in this silicon structure the unit cell, and that is the unit cell that forms the crystal from silicon atom. Here what might be still not obvious, that you see one of the Breve lattices that was shown in the previous slides, and that's because the base, it's not a single atom, but the base of silicon crystal, it's made of 2 atoms. So the blue atoms will be, let's say, just showing the one part of the base, but in fact the base is the blue atom and green atom. So we have a blue atom at each corner and also at each face. So in the front, behind, actually what is missing, this one should be also colored blue, and then that would fill all the faces and all the corners. So like that we construct the silicon unit cells made of the base with 2 silicon atoms, and this translated by the primitive vectors builds the lattice, but because we talk now about the atoms and the base, that gives us the actual crystal. What is then next step to look at? We will analyze that unit cell for the silicon in terms of planes, but first let's have a look at the planes in a crystal in just 2D. So what is the crystal plane? We can have, for example, a plane like that, and the plane has certain distance d that is calculated with the lattice vectors. We can have another plane that it's like that, or like that, like that, like that. In fact, a huge number of different planes. For the infinite lattice, we can talk about infinite number of planes, of course. For the cubic system or 3D system, we can also make the calculation of what will be the distances between the planes, also not only on 2D, but in 3D in the volume. So when we think about the volume, and specifically about the silicon crystal, we have also a huge number of planes, but there are 3 planes that are in particular interesting. This will be so-called 100, 110, and 111. So there are some names and, let's say, the ways how to describe the crystal planes when we have the certain unit cell, how to describe so that we can talk about it and about the crystal orientation. So these numbers have meaning and designations coming from that, so from the orientation of the vectors that define the plane. And There are also other planes, but these are the most interesting. And for example, for 110, we will have the smallest amount of fixed charge at the surface. And because of that, there will be preferred plane when we fabricate the MOSFET transistors. So if we have a starting raw material, and it has to have already a known orientation. So when we grow the crystal, we need to know, we know that it will be a big rod of silicon that later we slice and we cut. And we need to know from the start, when we cut the wafer, what will be the crystal orientation that we have in the end, because that defines some properties. So the fixed charge, which is then the source of noise in MOSFET transistor, that's one of the properties, but there are different other properties also technological, because in the different directions, the doping will be, the dopant atoms will be propagating through the structure differently, and the doping profiles will be also different. So that's one of the reasons why it's important to talk about and understand these planes in silicon crystal. So exactly what we were just talking about is this electron that no matter in which place we find it, it will, in the lattice, because of the periodicity, it will see the same conditions, the same potentials, for example, of the lattice. And because of that, we are not talking in the lattice, in the periodic structure, about the location, where the x dimension, but we are talking about the planes that are seen as the condition of the silicon, let's say, the charge carriers, for example, in the silicon. And to talk about that, we will speak about the reciprocal lattice, where from direct lattice, we go to reciprocal. So from a set of points, we move to talking about set of planes. And therefore, we move from the real space to this so-called K-space, the reciprocal space. In this reciprocal lattice, the vectors, they relate to sets of planes in the real space. So those planes that we could see that in 2D, we can create many planes of the 2D lattice. And now we will be talking about the sets of planes. The length of the basic vector that we were seeing, for example, the primitive vector, when we talk about Breve lattice, is then 1 over length in the real space. Or if we talk about 3D, then the volume will be 1 of the volume in the real unit cell. So in other words, we will see an example that every dimension that it's larger in the real space, in the inverse space, it's inversely proportional. So let's have a look how this inverse room is constructed. We have the 2D real lattice. And we can take, for example, this plane with 1 over d. So d is the distance between the two planes. And 1 over d, that will be the vector that constructs points in the inverse space. We can then take another one, for example, the other, which is the perpendicular, and then we have another distance. So the distance will be, if it's not a square lattice with the identical primitive vectors, then it will be different number, which is 1 over d. And that constructs the next point in the inverse lattice. We can have also any other plane which has certain dimension, the distance between the two planes that connects the points in the lattice, and this will create a new point in the inverse room. So every plane, it's a single point in this inverse lattice. And we can construct the complete inverse space, where instead, where we talk in the real space, we will speak about particles and in its wavelength. in the inverse space, rather than dimension x, y, we have these wave vectors k, and it's related to the real space, the wavelength, as 2 pi over lambda. So again, it's the inverse relation. So now the wave is described in terms of wavelength per unit distance, rather than just the simple wavelength, which would be the distance per period. So having already this, the wave vectors, let's step back to talk about the energy and the momentum relation. First, what we know from the classical mechanics. The kinetic energy is described by the mass times the velocity squared divided by 2. And we can plot the kinetic energy as a function of velocity, and it will be different depending on what's the velocity, what's the actual velocity, and what's the mass. But we also talk about momentum, right? And the momentum is defined as mass times the velocity. So the kinetic energy alternatively can be expressed in terms of momentum. And so we can make basically the same plot, but instead of function of velocity, function of momentum. So kinetic energy as a function of momentum. And this kinetic plot as a function of momentum is what we are talking about also in the quantum mechanics. So we will have kinetic energy as a function of momentum. The kinetic energy is again momentum divided by 2 divided by mass. But what we have to remember in the quantum mechanics, there is an important difference, is that the particle energy cannot be continuous. So we have some discrete levels and not continuous. Then for the free electron, we can write that the momentum is the h bar times the wave vector. And the kinetic energy also can be described when we take into account in the first expression as in terms of this wave vector. And the wave vector is what we have seen as the vectors of the inverse lattice. So that's the connection between the concepts. I'm not going to any much details, but in order to understand later the EK diagrams, or at least to understand what we are looking at, I think some minimum information about this concept is necessary. So that would be for free electron, and what is true in any case is that this, what we have seen already, is the wave vector is proportional to 1 over lambda. And now if we take into account the fact that the lattice is a periodical structure, we can also write the expression for the mass of effective mass of our charge carriers, which is related to the second derivative of this kinetic energy as a function of the wave vector. And here we come to the EK diagrams. The left-hand side plot doesn't stop. So basically, when you see the silicon, memorize that. So we have on the left-hand side the silicon, this one, and on the right-hand side we have gallium arsenide. What we see here is the diagram of energy as a function of the wave vector. So we think about the planes of the silicon, and the bottom red line. Let's look at gallium arsenide because it doesn't move. The bottom is the upper energy of the valence band, and the blue one is the bottom energy of the conduction band. At the k equals 0, we have the top of the valence band and the bottom of the valence band exactly overlapping. So they are, let's say, in the same position for the wave vector. In case of silicon or germanium, we can see that for silicon, the bottom is somewhere here, for the conduction band, and the top of the valence band is somewhere here. So what is necessary is to change the momentum, because K is related to the momentum. In order to move from valence to conduction band, the charge carrier actually needs momentum change is involved, which is not necessary for gallium arsenide. And this is what makes the difference between direct or indirect band gap, whether there is the change in momentum or not involved. And also, what is interesting when we consider the wave vector and the energy, second derivative gives us the relation to the mass. And because it changes with the wave vector, for different crystal orientations, we will have a different effective mass. So for example, for holes, we have the different planes that we can define, and the effective mass will be different. Actually, for electron, also same happens, but this is just an example. So for these two planes. So for, in addition to the change in the effective mass, which is defined by the steepness of those energy levels in the EK diagrams, we have the indirect and direct band gap. So in case of the indirect, which is the silicon or germanium, we will have the change in momentum. So it's electron-phonon interaction, and very unlikely to have three particles interaction, electron, phonon, and photon. So that's why we have mainly heat emission and very extremely small probability of emission of photon. Whereas in the direct band gap semiconductor, we don't have the phonon interaction, but it will be electron-photon interaction. And that's why in gallium arsenide, it's a material that is known for photodiodes, because with recombination, we have emission of a photon. So that would be the important conclusion, also going through the step-by-step to the EK diagrams to get to the point that we have those two different types of semiconductor with indirect and direct band gap. And also the important dependencies on the planes of the crystal that we work with. So in summary, for the crystals part, you could see the mathematical concept of the crystal, actually of the lattice that later forms crystal. In order to have crystal, we need to have lattice, but we also need to have a base. And base can be single atom, it can be a group of atoms, it can be a molecule. Then for the silicon, we could see some examples of the typical planes that are used for silicon fabrication. But if we want to talk about inverse space, the inverse room, and go as far as the EK diagrams, we need to consider all the different possible planes that form the inverse room. And then in the EK diagrams, what we learn from that is that in silicon, we have the indirect band gap. That means it involves also momentum change, which is not the case in case of gallium arsenide. So gallium arsenide recombination is related to the emission of photons. And one more important and interesting conclusion also from EK diagrams is the effective mass. Effective mass changes with the orientation of the crystal, the direction of the wave propagation. So this is something that we might also have to consider when analyzing some more complex problems of semiconductor devices. That's it for today. Thanks for your attention.
You're the signal in my static hum, a perfect match we've overcome. Wires cross, but we still